motion without dampening. Okay, that's what makes it simple, is that we don't have dampening. So I have this problem here where let's see, you have a okay, we have a weight. Now you have a problem exactly like this in the weather sign. The only difference is that your numbers are probably going to be different. I mean, you could look out and get the same numbers I have, but here where we got 6 inches, you may have something like 4 inches or 8 inches. Okay, so we have a mass that weighs 24 pounds. All right. So we're actually not given the mass, right? That's not the mass. That's the weight, right? Pounds is the weight. So, a little bit of physics here. Yeah. Let me take a big piece of paper. Okay. So we have a mass that weighs 24 pounds, right? And let's see. So, well, first of all, our differential equation, right? A differential equation is m double dot, right, plus kx is equal to 0, right? That's the differential equation for a spring mass system and without dampening and without a driving force, right? There's no dampening here, no driving force. Now, if this was an in-class exam, I'll give you the differential equation on the exam, being this is not a physics class. But your exam is open book, so you have all the equations, everything you need, in my notes. Okay, so first of all, this is the differential equation, right? So the first thing we need to do is figure out what the mass is and what K is, right? We got to figure out what the mass is and what K is. Now we're told that the weight is 24 pounds, and it stretches the spring 4 inches. All right. So we also know that that the force, right, is equal to K times the X, right? This is Hooke's law, right? So in other words, if I stretch out, that's going to be my spring constant, okay? Right? The spring constant is just the force divided by the distance. And I think your book uses S. Let's use S when you stretch it out. Don't have an eraser here. Now, there's a couple of things I want you to be careful about. Is the units, right? This is where students make a mistake, and I normally take off very little, but makes it harder for me to grade because I have to see whether you did the units wrong or whether you did the math wrong. But okay, so we stretch a spring 4 inches, right? Now, when we're dealing with the Ingalls system, this has to be in feet, right? So 4 inches, right? So S is equal to 4 inches, right? But that's equal to a third of a foot, right? That's equal to a third of a foot. And it's pulled down, right? The force here, we're told that it's pulled down. The weight weighs 24 pounds, right? The weight weighs 24 pounds. So I got 24 pounds divided by 1/3, right? To get what K is. And don't worry about the negative sign. When we put it, because we've already taken the negative sign into account when we brought it over to this side of the equation. So, so what does this become? This becomes 72, right? So my spring constant is 72 pounds per foot, right? Now remember, the spring constant has to be in units of pounds per feet, or it could be in terms of newtons per meter, right? So, okay, so that's my spring constant. So now I found what my spring constant is. Now I got to find the mass, right? Now we're told that the mass weighs 24 pounds, right? So to find the mass, right, remember now the weight, let me put it up here. The weight is equal to the mass times the acceleration due to gravity, right? That's what the weight is. So the weight in this case is, I have to find the mass. We found, so we got the weight is equal to m times g, right? So So W divided by G, let me know if I go up the page, is equal to the mass. So this is going to be 24 divided by 32, right? 24 divided by 32. And that should be, let's see, I can write that as 3/4, right? Divide everything by 8. All right. So once again, this is our differential equation. So in these problems, you're going to be given words and you're going to have to figure out what the weight is, right? Or the mass. You have to figure out, in this case, and sometimes it may be the opposite, but you may be given the mass. Yeah, in some problems you could be given the mass, but here we're told what the weight is. So we got to divide by G. A hint is they gave us the acceleration due to gravity, right? So you have to divide by G to get the mass, okay? And then when you pull it down, right, the weight of 24 pounds is what's pulling it down. So that's the force that's acting as pulling it down. And remember now, this is students make a lot of mistakes if they divide by 4, right? You have to convert this to feet. And I think I do give you a problem where it's in inches and you have to convert it to feet. Okay. So, all right. So now, this is the differential equation. So now I have what the mass is, I have what the spring constant is. So my differential equation is 4/3, right? 3/4 x double dot plus 72 x is equal to 0. Okay, 72x. And then let's see, I can write that as x double dot plus, I think you can write this as 96. Yeah, right, multiply, divide this, yeah. But remember, you can write this as 96x, right? Multiply both sides of the equation by 4/3. Okay. What about the initial conditions? They tell us here, let's see. Initially, the mass is released from rest from 0.6 inches above the equilibrium position, okay? So it's 6 inches above the equilibrium position at rest. So it's 6 inches above. So that's going to be minus 1/2, right? Hope everybody understands this. Remember, we take positive direction to be down, right? Positive direction is down. So, so if I'm releasing it from rest, 6 inches above the equilibrium position, right? Remember, I have to convert this to feet. So 6 inches is, so this will be 1/2 of a foot, right? 6 inches is 1/2 of a foot, right? And then the minus sign is because I'm above. All right, so that's my differential equation. Now, this is real easy to solve, right? You could, the solution to this differential equation is just going to be, well, let me do this. It would be m squared, right? Plus 96. You could do it this way. But if you immediately write down, like the square root, this would be plus or minus. So this is going to be plus or minus, let's see, this 36, this is the same as 36 times 4, right? Right, this is the same as minus 36 times 4. That's not right. This could be written as 16, yeah, 16 times 6. Let's see, yeah, this is 16 times 6. 16 times 6. And then I can write this as the minus sign here. I can write this as 4i times 6, right? Any question? So, so what's my solution now? What's my solution? Now you could just immediately take the square root of this, right? I have no problem if you immediately take the square root of this and put that in here. So, so this would be x as a function of t is going to be c1 cosine of 4 square root of 6 plus c2 sine 4 times the square root of 6, right? Everybody got this? Everybody understand this, right? So, okay, so that's my solution to this differential equation, right? And if you wrote on an exam, if you wrote it as the square root of 96, I guess that's okay. You don't have to simplify it. I wouldn't mark it wrong if you just left it as the square root of 96. But if you made it 96, I'd have to take points off because you don't, you need to understand that, that this is the square root of this, square root of that number. All right. So the next part of this was now to apply the initial condition, right? We're told that it's at rest. All right. Let's see. Let me get another sheet of paper here. Let me get rid of this here. Try not to waste so much paper. Okay. So, all right. So I have this. Let me just copy this over. Okay, and we're told that, let's see, the initial condition, we're told that it's released from rest. So it's released from rest, and then the time t equals 0, the velocity is 1/2, right? Okay, so now I got to apply the initial conditions to get C1 and C2. So C1 is going to be really easy. This is going to be 0 is equal to C1 times, when I put 0 in here, this is just going to be 1, right? And then plus C2 times 0. Okay. Let's see something for a second.
Professor?
Yes.
So is that cosine for
wait a second.
E then?
It starts from rest. I got this backwards. It started from rest. I knew I'm not doing it wrong, but just hold on one second. It starts from rest. It starts from rest, right? So so the initial position is minus 1/2, and the velocity is 0. Okay. All right. The question? Did someone have a question?
There's no variable t in that solution you have up there.
Thank you.
Right. Thank you.
Okay. All right. Yeah. I guess once I started taking when I started taking the derivative, I probably would have seen it. Okay. So okay. So this is going to be minus 1/2 is equal to C1, and this is going to be 1, and then this is C2, and this is 0, right? So so I'm getting here that that C1 is equal to minus 1/2. Okay. All right. So all right. So now C1 is minus 1/2. I actually happen to know that. Okay. So anyway, so let's take the derivative of this. When I take the derivative of this, I'm going to get 4, right? And this is going to be minus, right? C1 sine, right? And then this is going to be plus 4 square root of 6 C2 cosine of, right? Cosine. All right, so now, but this is 0, right? So this is 0. So this is going to be 0, right? This is 0. And then, so then I'm getting that plus 4 square root of 6 times C2 times 1, right? So this is telling me that C2 has to be 0, right? C2 is 0. All right, so Right, so C2 is 0. So my final answer for this problem here is, let's see, this is going to be -1/2 cosine of 4 square root of 6 t. Okay, so that's the final answer. Hopefully that's what I got in my notes. Let's see, it's on the next page. 6. Okay, so that's okay, so here's the final answer. Okay, now there's two things I want to two other things. I want to talk about the amplitude and the period. Now this is something that you should have learned about amplitude and period when you took pre-calculus, right? So the amplitude here, we define the amplitude as just the magnitude of this number. Okay, so the amplitude is just equal to 1/2. And once again, it's not -1/2. It's the magnitude of this number, right? Because it's going to vary. If I actually, some places I have graphs of this. So the amplitude is going to be 1/2. The period, all right? When this repeats itself every 2 pi, that's the period, all right? So in this case here, the period is going to be 2 pi times 4 square root of 6 times t. That's what the period is. Okay. So so in this case here, right, the period t, this is how often it repeats itself. It's going to be 2 pi 4 divided by the square root of 6. So that's our period, right? This is our amplitude, and that's our period. All right. So you will have on the exam, I think there could be a problem where you have to determine what the amplitude and the period is. All right. Any questions? Now, sometimes determining what the amplitude and the period is actually more complicated, especially, well, for the amplitude. So let me talk about that. Now, see, in this case here, in this problem here, C2, right, C2 turned out to be 0. But what if we have C1 and C2, and I want to know what the amplitude is? Okay, so we're going to do a little bit of trigonometry now. If we get a problem where we have C1 and C2, we still want to be able to determine what the amplitude is. So we're going to do some trigonometry to figure that out.
Yes, sir, I have a question.
Sure.
I'm a little unclear as to when you use hyperbolic functions versus the regular cosine and sine.
Oh, okay. Yeah. Gee. Well, it turns out that, the solution to this different, if I had this, right? Let's say this is minus 4x, right? It turns out that the solution to this differential equation, I could write it as e to the 2x. In other words, C1. Okay, let's make this t plus C2 e to the minus 2t, right? This will be a solution to this differential equation. But you can also write this solution in terms of, we could either, we're dealing with exponents, but you can also write this in terms of C1 cosine, hyperbolic cosine of 2t plus C2 hyperbolic sine of 2t, right? And it turns out that, if you take a look, I actually have this in my notes. I think I have it in my notes. I think I put it on Blackboard. I guess we're getting a little bit diverted, but it's actually a little important that students are afraid of hyperbolic functions. Did I put it in here? Well, why don't I spend a minute tomorrow talking? I have some notes that I can point you to. But these are two different ways of expressing the solution to this differential equation in terms of sine and cosine, right? You'll see that this is a solution, okay? And the only thing is that when you find the constants, you'll actually get, I actually have it in my notes. I guess maybe I didn't put it on Blackboard, that that these are just two different forms. And when you put the constant in here, if you were to graph them, you end up getting the same exact function. But we're going to deal with exponentials, but we can also deal with hyperbolic functions, right? I probably spending a little bit too much time, but maybe tomorrow, if we have some time, I can talk more about that. But anyway, did I help you a little bit with your question?
Yeah, thank you.
Okay. All right. So I want to do a little bit of trigonometry now, where and you can follow along. What I'm doing here is in my notes. It's in
No, 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 no. No, 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 no.
Hold on. What's no? I guess someone has their speaker on that doesn't need to. Okay. All right. So what I want to do now is, let's say we have we do a little bit of trigonometry. Let's say we have this equation here, right? This is our solution. You know, any spring mass system without dampening, the solution is going to look like this, right? The general solution is going to look like that. Where in this case here, you know, the differential equation is written like this, right? That's a differential equation. I'm calling this omega squared, right? And this would be the solution to this differential equation. Now, we want to be able to write this in a form that looks like this, because with these two, well, we'll see how to find out what the amplitude is. If you have C1 and C2, how do you determine what the amplitude is? But you sometimes want to write it in this form. Now, if you've taken physics, I don't know why it's different, but most math books, when they do this, they'll write this equation in terms of sine. And physics books, at least the physics books I have, they write it in terms of cosine. But it really doesn't matter. I mean, in this book here, how many people have seen this written in terms of cosine when they took a course in physics? Has anybody seen this written in terms of cosine? Okay, well, all right. All right, so what I want to do now is I want to draw myself a little diagram here. All right, and I'm going to call this C1. I'm going to call this C2. This is some angle phi. And then we all know that the hypotenuse here, if this is a right triangle, this is going to be a C1 squared plus C2 squared. Okay, this, what I'm doing is in my notes. All right. And when you look at this, we can see that the tangent of the angle phi, right? The tangent of the angle phi is equal to, well, let's see. Well, let me do it this way. There's two ways to do it. The tangent of phi is, we know the tangent is equal to the sine over the cosine. But if you look here, the cosine of phi, right? This is going to be the same as C1 over C2, right? I can write this as C1 over C2, right? Which means that the arc sine of C1, or the inverse, is going to be equal to phi. Okay, let's see. Maybe I skipped a step here. Let's see. Does everyone see this? Well, let me, I think I skipped a step. Sine, right? The sine of phi. I mean, this is correct, but I skipped a step. The sine of phi is going to be equal to C1 over A, right? Everybody sees that. Sine is going to be equal to C1 over A. And the cosine is going to be equal to C2 over A. right? So therefore, A times the sine of phi is equal to C1, and therefore A times the cosine of phi is equal to C2, right? All right, so when I put that in here, right, the sines are gonna, the A's are going to cancel, right? And I'm going to get C1 over C2. So that's how I got this, and then I take the inverse of both sides, and that's how I got this. All right, this is the important. This is going to be the important formula, okay, on how we calculate what phi is. All right. Okay, with C1 over C2. All right. So now, let me know if I go up the page. So we have. So this is the equation we have. And this is the way your book does it. Okay, so you remember the trig formula. I can write this as this, right? I'm going to rewrite this as A sine. Remember now, C1, right? C1 is equal to A sine of phi from the diagram here. All right, and then I got cosine of omega t, and then C2 is equal to cosine of phi times sine of omega t, right? Oh, I forgot the A. Forgot the A. Okay. So now, let's see. Well, I'll factor out the A. So now I'm getting sine of phi cosine of omega t plus cosine of phi sine of omega t. Okay. Now, remember the trig formula that, let's see, we have the trig formula that the sine of, I'll call it beta. I think that's what I call it. Beta plus alpha is equal to the sine of beta times the cosine of alpha plus the cosine of beta times the sine of alpha. Okay, remember this, I guess when you took pre-calculus, you probably should have learned this, or even in high school, this trig formula. Okay, so let's see. So now what? Okay, so if I compare these two, all right, if I compare these two, let's see, what did I could write that in place of beta and alpha, right? In place of beta and alpha, I can write this as now the sine. Let me do this. The sine of yeah, okay, I'll put it this way, even though we write it the other way first. That's equal to, it's equal to what I have here. It's equal to, in other words, I put the A here, put the A here, right? I'm just using this formula. So in place of the, where I have the beta, I'm putting the phi, and where I have the alpha, I'm putting the omega t. So I'm getting this now is equal to A sine phi cosine okay. So so there we have it. I'm just showing you that this here now, I can write it like this. And normally when we write this though, we write it with omega t plus phi. Okay. All right. Now, all right. So that's our formula, right? And we have A now. So here's what's important. So the amplitude A, right? Depending upon the constants, the amplitude A will be the square root of C1 squared plus C2 squared, right? That's what the amplitude A is going to be. And the angle phi is going to be the arctan of C1 over C2, right? Well, now you got to remember the C1. Now this in this case it does matter. If you're calling this C1 and C2, you got to remember that C1 is the constant in front of the cosine, and C2 is the constant in front of the sine. All right. Now this is a case where you do need to call this. If you're going to use this as C1 and C2, you do have to call this C1 and this C2. Or another way, if I call this A1, I have to call this. This has to be A1, right? So in other words, whatever I have here on top, you can call it whatever you want, but the key thing is whatever you have here on top has to be in front of the cosine. And whatever you here have on the bottom, that has to be what's in front of the sine. You'll get it, you'll get the wrong angle if you do it the opposite way. Okay, so I hope everybody understands that what's in front of the cosine has to be on top, what's in front of the sine has to be on the bottom. Okay, now if you're in the first quadrant, now here's where it gets a little bit tricky, and hopefully you remember some of your trigonometry. If it's in the first quadrant, it's very easy, right? You just take C1 over C2 and, to get the angle phi. The amplitude's never a problem. You just take C1 squared plus C2 squared, okay? So the amplitude's not a problem. But phi, we got to be a little bit careful. Now, let me explain what I mean by that. If I'm in this quadrant, right? Let's say I'm in this. Okay. Let's say now, see C1 and C2 could be negative or positive, right? So if let's take the example. Let's see what. Let me just check something here. What's that I put in my notes? Okay, let's see. Okay. All right. Let me. I'll do like it's in my notes. So so let's say we have this. Okay. So let's say we have this. All right. So all right. So this, what's in front of here now? What's in front of the cosine? This is going to be okay. So this is going to be my C1. So in other words, this is going to be the arctan of C1 over C2. The easiest way to do this is to use the in this case it's positive. This C1 is positive, and this is going to be negative. Okay. So the easiest way to do this is to recognize the fact that that what we're dealing with here is that we're in this quadrant. Okay. We're in this quadrant, right? Because of let's see, maybe I should okay. So let me write this. So C1, let me write this. C1 is equal to 2/3, right? And C2 is equal to minus 1/2. No, excuse me, minus 1/6, right? C2 is equal to minus 1/6. So so what is but remember now, this is actually the sine, right? This is the sine. So the sine is positive and the cosine is negative, right? Right. So we're in this quadrant, right? Now, the easiest way to do that is you recognize the fact that you're in this quadrant, right? You have to understand that we're in this quadrant. And so when I calculate this angle, right? But I don't worry about the sine. I calculate this, right? And I get the tangent. Let's say is 2/3 over 1/6. What does that come out to be? This comes out to be 4. I'm looking at my notes. This comes out to be 4. Okay. Now this is the reference angle. What I just calculated, I didn't calculate my angle phi. I calculated, remember the reference angle? I calculated the reference angle. If you ever had me for trigonometry, you would know this backwards and forwards. This is the reference angle. So I'm getting the reference angle. But the angle I want is this angle. This is the angle phi, right? This angle is the angle with respect to the x-axis. And keep in mind that this x is not the same as what we're talking about here with the x-axis, right? So this is the angle phi, not this angle, all right? So you have to figure out, based on the values of C1 and C2, you have to figure out what quadrant you're in, all right? And then I'm going to get the reference angle. And then once I know what quadrant I'm in, it's going to be, in this case here, right, the angle phi, right, this angle phi is going to be equal to, it's going to be equal to pi minus the arctan of 4, right? It's equal to pi minus the arctan of 4. So the thing is, when you're in the first quadrant, it's a lot easier because the reference angle is equal to the angle phi, and you just take the ratio of the two numbers. But if you're in one of the other quadrants, you have to figure out what quadrant you're in. Like if I'm in this quadrant here, right? If I'm in this quadrant here, where in this case here, both C1 and C2 are negative, right? So here's the way to look at it. If both C1 and C2 are negative, you're going to be in this quadrant, right? You're going to be in this quadrant if, let's see, if C1 is positive and C2 is negative. All right. Let's see. This is C1 is what? C1 is not. No, I said that backwards. So if C2 is positive and C1 is negative, you're going to be in this quadrant because this is the sign. All right. Remember too, all students take calculus, right? So all the trig functions are positive in this quadrant, right? It's only sine and and its inverse are positive here. Here you got tangent and cotangent. Here you got cosine and secant, right? So okay. So let's see. Let's see something else. I want to try to find something here. Let's see. All right. So here's I just want to, let's see here. Just go over my notes here, right? This is all students take calculus. So the C1 here is positive, right? This is the sign. So the sign is positive. The sign is positive in this quadrant. Right? Because this is positive and this is negative, right? I know I'm in this quadrant, right? So so once again, the best thing is just don't worry about the signs, right? That's the way you do it. You don't worry about the signs. And then you figure out, and because it's going to give you the reference angle, right? You don't worry about the signs because it's going to give you the reference angle. And then you have to figure out, like if I'm in, remember, the reference angle is always with respect to the x-axis, right? So this would, I'm going to get the angles I'm going to get at this angle and this angle, right? So when I'm in this quadrant, it's going to be my reference angle plus pi, right? When I'm in this quadrant, it's the reference angle plus pi. When I'm in this quadrant, it's going to be 2 pi minus the reference angle. Because when I'm in this quadrant, the angle I want is this whole angle here, right? This is my angle phi. All right. I hope it's clear. Sometimes we forget our trigonometry. So that's why I wanted to review this. Okay, any questions? All right, maybe this is real easy for everybody, am I right? Okay, everybody's confused? Okay, so, so I have a number of problems. Let's see. Okay. All right. Well, if there are no questions, I'm going to go on now to damp motion. And you can take a look. There's more example problems, you know, in my notes. But let's go on to dampening. Okay. And then we'll do driven on Monday. All right. So the differential equation for dampening is I guess I'll write it like this way sometimes. So we're going to assume dampening that's proportional to the velocity. That's what this is. This is the velocity. So, you know, I can write it like this. All right. So this is the differential equation. This is some, we have the mass, right? This is some constant that's multiplied. So we're saying that the dampening force is proportional to the velocity, and that and then we have our spring constant times x. So this is the differential equation that describes harmonic motion. This wouldn't be simple. We don't call it simple when we got dampening, but this is harmonic motion with dampening. All right. Now I'm going to do something that I actually think this, or there should be two here. So let's see. I can write this like this. Right. And then we define, this is in order to classify the different types of motion you can have when you have dampening, right? You can have 3 different types of motion. So it's standard to come up with these parameters where I say that 2 alpha is equal to beta divided by m, and that we're going to call omega 0, which is the angular velocity, is going to be k over m, omega 0 squared. So it's common to use these 2 parameters, okay? And then so instead I can write the differential equation like this. Right? I can write the differential equation like that. And then okay, then immediately we know that the characteristic equation, or the auxiliary equation, right? This would be m squared plus 2 alpha m, right? I'm just writing it plus omega 0, right, is equal to 0. Okay. All right. So so now to solve this, right, I just use the quadratic formula, right? So the quadratic formula tells me that m is going to be equal to, and this is why we do the 2 alpha. M is going to be equal to 2 minus divided by 2, right, plus or minus, and then this is going to be square root. This will be 4, right? When I square this, 4 alpha squared minus 4 omega 0 squared divided by 2, right? And then we could simplify this. Well, let me put it up here. Let me go up here. Let me know if I'm going out of the window here. we could simplify this as minus alpha, right? Because the 2's cancel. Then I get plus or minus. Now this I could factor 2 out of here, right? I can factor the, right? I could bring this out as a 2. And so I get plus or minus the square root of lambda squared minus omega 0 squared. That's a lambda, not an x. Okay. And so this is my m's, all right? Minus lambda plus or minus square root of lambda squared minus omega 0 squared. Okay. So, so we have different cases now. We could talk about case 1, where, once again, we look at the discriminant. So if this is lambda squared minus omega 0 squared, if this is greater than 0, we refer to this as being overdamped. It's called overdamped, right? Overdamped. That's case 1. And this is greater than 0, it's overdamped. You're going to see that you can end up getting exponentials. And we have case 2, where when this is equal to 0, yeah, this is what we call critically damped. This is critically damped. I spelled critically right. And then we have case 3. You know, it's all much neater in my notes. Case 3 is lambda 1, lambda squared minus, once again, the same thing, but this times it's greater than 0, less than 0. This is greater than 0. This is less than 0. And this is what we call underdamped. So we'll take a look at these different cases. So now, okay. So now, if we had case 1, I sometimes, it's a way of classifying it, but I'm going to show you that it's actually easier to solve. I'm going to show you a way to solve another way to solve it by just using this formula now. So now we have M1, M, this is case 1. M is equal to minus lambda plus or minus the square root of lambda squared minus omega squared. Okay, so what's my solution? Well, my solution is just going to be this. It's going to be C1 E, and then it's going to be minus lambda, right? Minus lambda, let's see. Got to put a parentheses here. Minus lambda plus the square root of lambda squared minus mu 0 squared times t, right? Plus C2 e to the minus lambda plus or minus. Well, I don't want plus or minus. I have the plus there, so now, right, remember, this is plus or minus. So I got the plus here, so now I got a minus here. So I got a minus here. Square root of lambda squared minus omega 0 squared times t, right? So this is my, once again, this m now is not the mass, right? This is, this m is what we've been using for the auxiliary equation, right? For the roots of the auxiliary equation. So this m is not the mass. Okay, so in case 1, if, you know, once I write the differential equation in terms of lambda and omega 0, then this is the solution, right? Case 2, case 2 is just m is equal to minus lambda, right? Case 2, remember case 2? Let's see. This is 0, right? This is 0. For case 2, this is 0, so I'm just left with minus lambda. So for case 2, right? The solution is just going to be this. It's going to be C1 e to the minus lambda t plus now C2. What do I need to put here? I need to put a t here, right? T, right? Because I need another independent solution. E to the minus lambda t. All right. You know, you can also write it as, yeah, you can also write this. I think in my notes, I wrote it like this. I'm looking at, yeah, my notes, I wrote it like this, but just so you know, it's the same thing, right? You can write it like this. All right. So this is what we have for case one. So once you write down the differential equation, this is going to be your answer. If you know what the lambda is and what the omega is. And case three, we can do a problem after this. I hope we got how much time we got. Very good. Okay, so case three, let's do case three. Case three now is going to be imaginary. So case three is when you're going to get both of case one and case two, you get exponentials as your solution, right? You get exponentials as your solution. But for case three, we're going to get that m now is going to be equal to minus lambda. And now remember, now we said that it's negative, right? So I'm going to write this like this: omega 0 squared minus. We write it like that in reverse, because we're saying that that this here now is less than 0. So I can write it like this. All right. So what's the solution? What's the solution to so the differential equation? If this is my m value, right? This is the roots of my auxiliary equation. Then the solution to this is just going to be e to the minus alpha t, right? And then I can write this as the cosine c1 times the cosine, and then this would be the square root of omega 0 squared. Okay. By the way, I think your book does not use omega 0. I think they just use omega. I want to use omega 0. Just we're probably not going to get to it, but if we get into resonance, I want to show you that when you have a driving force, probably not going to get to it. I use omega 0 because when I do resonance, although I haven't been able to get that far in this every time I taught this course, but it's not required either. That I use omega 0 as the natural frequency, the natural angular momentum frequency, and I use omega as the driving frequency. Okay. And this is C2. I need a T here. Don't forget my T's. Sloppy. Okay. All right. So now we have the solution where we're actually going to get sines and cosines. So once again, for case one and case two, you're going to end up getting exponentials. Case three, you're going to get sines and cosines. And the Weber sign, I think you have at least one problem in each case. Okay, so let's do a problem now. Well, even before I do a problem, you know, I know that sometimes my handwriting is not the neatest. So I've spent enormous amount of time taking all my handwritten notes and put them in and using a tool called MathType, you know, to type everything up. I spent maybe a whole summer last summer just typing all this stuff up. Okay, so anyway, I just want to show you what some of the solutions look like. So when you have overdamped, a solution could look something like this. Okay, so here I put in certain parameters. You can look at this on Blackboard. I put in certain parameters so you can see what the overdamp looks like. So here are two possible graphs where if you have overdampening, the at most you can go through the equilibrium position only once, right? Either no time either you can't go through the equilibrium position at all, or you can go through only one. So here's an example of overdamped. These are two examples of overdamped, right? Where you can go through the equilibrium position. In this case here, it does go through the equilibrium position once. All right. So let's see. So then in my notes too, I have an example of critically damped. So this is what critically damped looks like. All right. And here's two examples of critically damped. And you have, once again, with the mass can pass through the equilibrium position at most one time. So when you're damped and critically damped, you can only go through the equilibrium position at least one time. And you do have like a problem in Weber sign where you have to find the maximum value. And, you know, so once you get the solution, you have to take the derivative, set it equal to 0. All right, maybe we'll probably get to a problem like that. And then finally, here's this is over. This is what I just did. And then when you have no, well, here's an example where you got no dampening at all, right? You have no dampening at all. And then, you know, this is simple harmonic motion. Yeah, this is simple harmonic motion. See, it's varying up and down. And here it's underdamped, right? This would be underdamped. And you can see that basically what you have is you have sines and cosines times an exponential. So it makes sense, right? You have a decaying exponential times sines and cosines. Okay. All right, so you have those graphs. Okay, so let's do a problem. See what time we got. Okay. Let's do a problem with dampening. And I think I want to do, let's see. You should look at all the problems I have in my notes. Let's see. I guess I'm going to do this problem here. Yeah, let me do this problem here because I want to show you. I want to show you what actually a way that I actually find a little bit simpler, but it's up to you to do it either way. So let's do this problem here. So this is, let me just take a look at one thing here. Let's see, is this, okay. I'm going to work it out, right? You all prefer me to work it out as opposed to just talk about it, as opposed to reading from the view graph, I assume. All right, that's not the
Yes.
way. Yeah. Okay, so let's see. I want to find this problem. Okay. This is 10. All right. Like I said, I have other problems, but let me do this one here. This one may be a little bit, well, it's hard to say. Okay. So all right, so here's the problem we want to do. You're able to see everything, so let's see. Okay, so we're told that we have a one kilogram mass. Okay, so this time we don't have to calculate the mass. So our mass, right, is 1 kilogram. So we don't have to calculate the mass. Mass is 1 kilogram. That's good. And we're actually told the spring constant. Okay, so we know what K and M is, so we don't need to once again, if in a problem, if you're given the weight in terms of pounds, you have to find the mass in terms of slugs, right? So they tell us what the spring constant is in this problem too. So this is going to be 18 Newton meters. So we got what the spring constant is. And we're told that it's submerged in a liquid that gives a dampening force that's numerically equal to 11 times the instantaneous velocity. Okay, so so my beta in this case is just 11, right? It's 11 times the right, 11 times the instantaneous velocity. So remember, it's going to be just if they tell you that it's 2 times or 3 times, that's what you choose for beta. All right. So now remember, now the differential equation is mx double dot plus beta x dot plus k equals 0. Right. So okay. So let's see. So I can put it in the form, right? I can put it in the form. Let me do it this way first. No, let me trying to see here. All right, let me put the numbers in. So this is just going to be, then this is going to be 18. Let's see, this is 11 x dot plus 18. Forgot the x here. Got the x. Okay. So all right, so that's my differential equation. Now so let's do what we just did, okay? But then I want to show you that you don't have to do it this way. It allows us to classify. In other words, what we just did, it allows us to classify the different types of simple harmonic motion. All right. So in other words, now remember now that we said that 2 alpha was equal to 11, right? And we said, so in this case here, well, remember now, yeah, we write it in this form, right? We write it as, yeah, we call this, we call 2 alpha beta, right? Remember that's what we just did. And then the omega 0 squared is equal to 18. All right. And so, all right, so that's what we have. All right. So, so then I can use the formula, right? The formula was, should I, all right, remember the formula is m is equal to, yeah, this would be 11 over 2, right? Plus or minus the square root of 11 over 2 squared minus 18. Right, so that's going to be my m. Let me just go, right. I'm just plugging it into this formula. That's all I'm doing. Let's see, this is, right, we're just plugging it into this formula here. So, okay, so this is telling me that, let's see, this is, okay. All right, so let's see, so we got, oh, this, yeah, okay. So let's figure out what this is. Let's see, this is going to be 121 divided by 4 minus 72 divided by 4. Okay. And so let's see. So we got n is equal to 11 divided by 2. There's a minus sign here. Plus or minus. Let's see. This turns out to be 49, right? This is 49 over 4, right? 121 divided by minus 72. This turns out to be the square root of 49 divided by 4, right? I actually think what we're doing right now is harder. I'm going to show you an easier way, right? After we do this. Okay. So, so let's see. So what do we get? So we get m is equal to minus 11 over 2 plus or minus, and then this is a 7 over 2 right? Plus or minus 7 over 2, right? So let's see. So I'm going to get, this is, when I have the plus sign here, when I have the plus sign here, what am I going to get? Let's see, 11, this will be 4 over 2, right? In other words, let's see, m is equal to minus 11 over 2 plus 7 over 2. So this is going to be minus 4 over 2, right? This will be minus 4 over 2, so which is minus 2, right? Which is minus 2. And then if I make this n is equal to minus 11 over 2, so now I use the minus sign, 7 over 2. So this is going to be minus 18 over 2, which is minus 9. Okay, so now I got my, so the solution is going to be x of t is going to be equal to c1 e to the minus, let me just use e to the minus 9t plus c2 e to the minus 2t, right? So once again, I'm using what I just showed you and then plugging it into the formula, right, to get what this is. All right. Any questions right now? Like I actually think there's an easier way to do this, but what we did, once again, the reason why I wanted to go through this process here is so you could classify, if you wanted to, you can classify whether a spring mass system is it's critical damped, over damped, or under damped. All right. So we needed to go through that process to do that. But so okay, so we did get this solution to the differential equation, right, by plugging it into the formula that we came up with here, right? This is our general formula, and then we have these 3 different cases. Okay, right? But if I was to solve this problem, I would just do it like this. This is what we have, right? We got n. Hope everybody sees this. And in my notes, I actually showed it to you too. But right, I could immediately write. This is what we learned, right? We know how to solve this. I can immediately write down what the auxiliary equation is, right? It's m squared plus 11m plus 18 is equal to 0. Okay, I could factor this. I could factor this into m plus 9, n plus 2, right, is equal to 0. So this is telling me that n is equal to minus 9 and n is equal to minus 2. Okay, so I'm getting the same answer, right? Okay, so so once again, you rewrite it like this, and then I have the formula, and you plug it into the formula. It allows you to determine whether it's critically damped, over damped, and so on. But when I solve this, if I had to solve this problem, I would just solve it by the method we learned when we solved homogeneous differential equations with constant coefficients, right? Right. We just write down the auxiliary equation, and if we could factor it, that's fine. If we can't factor it, then we use the quadratic formula. So either way, I'm showing you either way works. I think this is simpler than plugging it in and see here well, some cases this may be simpler, but notice it was a lot less work to figure this out than it was to plug it into the formula and then figure the number out here. But you do get the same result. Questions? All right, so let me just finish this problem though. Good, we still have some time. So we have to put in the initial conditions. All right. I'll give you a chance to do any work today. Okay, this was the last problem I was thinking of doing. Let's see what time it is. Should I do more? Okay. All right, let me give you a minute. So we have the solution to the differential equation. Um, I want you to calculate the constants, being that this is the last problem I wanted to solve. But let me give you a, I always like to give you a chance to do something. So see if you can calculate. So we're told that the mass is initially released from rest and 1 meter below the equilibrium position. All right. So I want to make sure you know how to write down the initial conditions based on the words. So write down the initial conditions and see if you can come up with C1 and C2. Now, when we have exponentials too, we can't, when we have exponentials, we can't put it in the form of an amplitude and a phase factor. Right? It's only when we have harmonic motion. All right, so see if you can come up with that. I want to look for something. It's kind of but, okay, let me go ahead and solve this. So we're told that in this problem here that it's 1 meter below the equilibrium position. So okay. So let's see. So 1 meter below the equilibrium position. All right. So this is just going to be 1, right? It's going to be equal to C1 plus C2, right? Right. So in other words, x of 0 is equal to 1 minute. Remember now, we're taking below to be positive, right? So it's 1 meter below. This will be 1, and then we're told it's from rest, so that would be 0. Okay. So now, so I get that 1 is equal to C1 plus C2. So now I have to take the derivative. So this is going to be minus 9C1 e to the minus 9t minus 2C2 e to the minus 2t. Okay, and this is going to be equal to 0, right? On this initial condition is 0. So this is going to be now 0 is equal to minus 9C1, right? Plus 2C2, all right? All right, so this is telling me that, let's see. So this is going to be C1. How come my notes are? Oh, okay. So I have to solve simultaneous equations here. All right. So let's see. What's the best way to do this? I'll multiply this equation by 2. Multiply this equation by 2. Let me know if I go off the page. So this is going to be now 2 is equal to minus 7C1, and then this goes to 0. So then I'm getting that C1 is equal to the C1 is equal to minus, right? Right. So I multiplied this equation by 2 and then added both the equations. Or you could solve this for C1 and put either way. All right, so that's what C1 is. So now I can get what C2 is, right? C2 is going to be 1 is equal to minus plus C2, right? Just putting the C1 into here, right? Putting the C1 into here. So now I get 1 plus 2 over 7 is equal to C2. So this is going to be, all right, this is 7 over 7 plus 2 over 7 equals C2. So this is going to be 9 over 7 is C2. All right, 9 over 7 C2. Okay, so so my final answer is going to be where was my C1? Oh, C1 minus 2 over 7 e to the minus 9t plus 9 over 7 e to the minus 2t. Is that right? Okay. So that's the final answer. Now there's another part to this problem where you have to find, so once again, this is a WebAssign problem that you have, but you know, I try to do the harder ones. So make sure you know how to do this problem, especially for the exam. I forgot what was actually on the exam, exact problem. But this is just with an initial, different, part B is a different initial condition where in part B, it's 1 meter below the equilibrium position. It also has a velocity, an upward velocity, right? So the upward velocity is going to be negative, right? So in I better hopefully I did negative. Yeah. So in part B of this problem, the initial position is +1, and the velocity at time t equals 0 is -12 because it's in the upward position. Remember, we take down to be positive. Okay. You know, it's unfortunate that we don't spend a lot of time. I think the courses that we take in Montgomery College, at least in the math department, it's unfortunate you don't get a lot of exposure to hyperbolic functions. And they're actually really important. I don't have this on Blackboard, but I can put it on Blackboard. But you know, if you have this differential equation here, does everyone see what I have up? You know, you could use hyperbolic functions instead of exponentials as a solution to a differential equation. So like this differential equation here, well, here's some of, you know, a hyperbolic function is really just, you can see here's the definition of hyperbolic sine, and here you have the hyperbolic cosine is down here. Here's tangent, and you know, these are the other hyperbolic functions. You know, when like just a few properties, the derivative of hyperbolic sine is cosine, hyperbolic cosine. Turns out that there's no minus sign here. The derivative of hyperbolic cosine is just hyperbolic sine. And then there's all, you know, there's identities just like you have with the trig functions where, you know, instead of cosine squared plus sine squared being equal to 1, you have hyperbolic cosine squared plus hyperbolic sine squared are equal to 1. But the important point I want to make is that your book just deals with exponentials when they solve the differential equation. But, you know, the general solution to this differential equation could be written like this, right? I can write it like this, or I can write it like this. I can write it in terms of these exponentials, or I can write it in terms of sines and cosines. And if I put in the initial condition, in other words, here, if I put in these initial conditions, you can take a look at this. I can put this on Blackboard if you want, but the point is that if I put in this initial condition, here's the solution I get, right? This is the key thing. If I put in this initial condition, this is the solution I get, right? It turns out these are both exactly the same, all right? And, you know, they're just written in a different form. And on the next chart, I show that they're exactly the same. That, okay, so this is, we take a look at this solution, all right? If I use the definition of hyperbolic sine and hyperbolic cosine, right? If I use the definition of hyperbolic sine, hyperbolic cosine, you can see it's exactly the same. So I just put the definition in here of hyperbolic sine and cosine in order to get it in terms of exponentials. And you see the two ways are just two ways of writing exactly the same thing. So you can see that this here is exactly equal to this when you substitute hyperbolic sine and hyperbolic cosine in terms of the exponentials. Okay. Now, whoever asked that question is probably maybe not going to ask the question again like that, but maybe not. I hope not. I hope not. Okay, so let's see. I guess we still got 10 minutes. We still got 10 minutes. Should we call it a day?
Sounds good.
I guess we got, well, not quite 10 minutes. Well, are there any questions? I'll be happy to answer any questions. And so there's no exam today because we didn't do, there's two things we have to do before the exam. One is we have to go over the driven. And the math is basically what you already know, okay? You already know the math. You know, if you know how to solve non-homogeneous differential equations, you know the math. So we're just going to do a little bit of applications of how to solve a non-homogeneous differential equation with constant coefficients when we talk about driven spring mass system. Okay, so the math you know already, and then we're going to talk a little bit about systems of equations, and then we'll have the exam on Tuesday. On Tuesday we'll start power series. Okay, well, hope everybody has a good weekend, and you know, I think it's, you know, some of the problems get a little bit longer. Okay. All right. So that's it for today.
Excuse me, Professor.
Yes.
I actually had a question before you go.
Okay.
It's actually a question on the WebAssign.
Okay.
I'm not sure where the step comes from.
Okay.
Uh,
okay. Tell me what problem it is.
4.4, number 4.
4.4, number 4. 4.4, number 4. Okay, I'm looking for it now. 4.4. Number 4. Okay. All right. Is this the problem you're talking about?
Yes, it's very similar.
You probably just have a different number here.
Yes. So the problem I'm having is why do we add an x to y of p1?
Oh, because see when you okay, the solution here to this, you have to have an x because you need a linear independence. So our rule is that let's see, I'm trying to think how best to that you see, if you can't have a particular solution that's linear dependent on the complementary solution. See, this is the complementary solution, right?
Right.
Okay. So I can't have a constant and I can't have an e to the minus 2x, right? So in other words, I have to assume a solution of this form. I have to multiply by x. See, let's see. Let me show you the rule in the notes. Okay, let's see. What did I do? Let me find something else. Okay. Could you Okay. Are you seeing now, the view graph that says non-homogeneous differential coefficients that has, consider the following?
Are you sharing it? I still see the PowerPoint.
Okay. Let's see. Okay, how about now?
Yes, I see it now.
Okay. You see now, the complementary solution looks like this, right? And here, see, I got this 4x here, right? You see, I got cosine of 4x,
Yes, I see
My
the
comp-
4x.
right? And my complementary solution here is 4x.
Right.
I can't assume a particular solution of cosine of 4x and sine of 4x. I can't. I need a linear independent solution. So instead, we assume a solution of x times cosine of 4x. Right? That's the rule. Okay? Because this will be linear independent and it works. All right? You see now here, if you take a look at this case, right?
Right.
The complementary solution is C1 e to the 5x, right? And C1
Right.
minus e to the 5x. I cannot assume a solution of this, right? Because this is not linear independent with these two. See, I got a e to the 5x, and here I got a e to the 5x.
Right.
That's no good. So I need to assume a solution of a x e to the 5x.
Okay.
Does that make sense now?
Yes.
Okay, now here's another example, right? In this case here, I have x e to the 5x,
X
Right.
e to the 5x. Right.
right? So I can't, and they also have a e to the 5x. So I can't assume a solution a e to the 5x or even a x e to the 5x, right? So in this case here, I have to assume a solution a x squared e to the 5x,
Okay.
right? Because I can't, I have to see, the rule is that if any y of p, right, if any of the particular solutions contain terms that duplicate in the complementary, then we must take our particular solution and multiply by x to the n, where n is the smallest possible positive integer that eliminates the duplication. Like this statement comes right out of your book, by the way.
Okay.
Okay.
I
Now, does
guess that
make
makes sense.
So
Yes.
if we go back now, if we go back now to this problem here, let me stop this and let's see. Go back to here. Yeah, if we go back to this problem here,
Right.
right? You see, this is what this, I can't have a constant, right? And I can't have, so
A
I have to
duplicate
assume
term.
b times a constant. I have to assume b times a constant. So this is what I have to assume is my particular solution, right? I can't duplicate a constant times e to the minus 2x. And I can't duplicate a constant. So this is what I have to assume.
Okay. Yeah, this makes sense.
Okay. Good.
All right. Thank you, Professor.
You're welcome. Other questions? I guess the people, yes.
So since we didn't finish, I guess 5.1, are you gonna extend the deadline in WebAssign?
It's not due this Saturday. Is it due next Saturday?
Yeah, I think it's set it to 31st.
Yeah, it's due. It's due.
No, I did do five. I did finish 5.1. I didn't think I finished 5.3. I didn't finish the. I'll take a look.
Oh, okay. So you said you finished 5.1, right?
Yeah. I finished 5.